familiar with these topics, so forgive me if I'm going to be too how to say, basic. But for those who are not familiar with power networks and renewables integration issues, I hope that this presentation will be interesting. So I'll go quickly through 4 different topics regarding transmission and distribution networks. The first one is, of course, introduction. The second part is quality of TSO and DSO service. Actually, my main intention here is how to measure, is the system operator or the network doing its business well? The third one is the story about ancillary services and problems that are appearing in the system with large-scale renewables integration. And the fourth topic is network planning. That is much more challenging than before. So before I go into these 3 specific topics, just few notes on the introductory part. So first of all, why is network important? This is, by default somehow clear, but the point is that actually this network in Europe, not transmission nor distribution, was initially designed for the situation we have today. It is not designed for large-scale market or distributed generation or large-scale renewables integration. All these networks actually started with larger scale construction maybe 60, 70 years ago, in total maybe 100 years ago. But definitely every single country was developed as a sustainable, self-sufficient network that was having only several links to the neighboring system just for the cases of emergency, not for any large trades, not for any large exchanges, not for any market activities. In the last decades, especially the last 2 decades, we have a rapid change in generation capacity and location. So we all learn at universities that large generation is economy of scale is much more efficient, much better. Now we are going in the opposite direction. We are pushing distributed generation, and of course we are introducing something additional to that, and that is introduction of user response. So far, those networks on distribution level were mainly passive. So the direction of the electricity wasn't just to the final user, but now we are changing even this aspect. Users can be active, can produce the electricity and inject it back into the network. So if you put it all together, it's really big change compared to the situation that was initially designed. As I said at the beginning, every single country was playing its own game with relatively low level of the links and interconnection to the neighbors. While EU activities and all these projects that we'll talk about are actually going into the opposite direction to prepare Europe as a copper plate, so we all play the same game on the same field. And the big move actually happened 2 years ago when 23 countries of Europe, these ones given in blue here, actually were coupled to one market, let's say, region. So if you bid or if you offer in one place, it automatically means that you are on the same platform with the same rules in all other 22 countries in Europe. This was a massive, big, huge change in European market, but also network operation. Just to remind you briefly on a history for those that are not familiar with it, the European network actually started to be, how to say, coordinated, harmonized in parallel operation 70 years ago. In 1951, the first association or union for coordination of production and transmission of electricity was formed, as I said, in 1951, combined of these countries, Italy, France, Germany, and other countries. At the same time, it was a Cold War. So on the other part of Europe, in 1960, Association of Eastern countries was also formed, where these countries were connected into synchronous operation, actually with the capability to exchange the electricity. These 2 regions were not having any possibility to exchange electricity. There were no links. There were actually a few HVDC links, but this is not important in the whole perspective. A few years later, So 1 year later, actually, Iberian Peninsula joined Western European part of the system. A few years later, Nordel was formed as an association of the TSOs or systems on the northern part of Europe. In 74, ex-Yugoslavia joined Western countries. So in 77, Greece also became part of UCPTE. So these 2 or 3 blocks were operating just 40 years ago, completely separated, completely isolated from each other, and there were no big opportunities. There were no opportunities at all to exchange electricity between them. In 1985, Albania was connected but not full member, and at the same time, UK area was also formed as a TSO association. And then a war in ex-Yugoslavia in 1991 resulted with the demolition of several transformer stations that resulted with the disconnection of part of the region to the island operation, actually completely separated from the rest of the world. In 1992, when Eastern Bloc actually collapsed, Romania and Bulgaria joined island operation of these Southeast European countries. So we had several colors at that time. In 1992, there were several blocks of countries that were operating separately in parallel operation to each other, but not connected to the others. And it actually happened that in 1995, Poland, Slovakia, Hungary, and Czech Republic were connected to the rest of Europe, while this right side actually continued to operate as an island operation. In 1997, submarine link to Northern Africa was installed, and we had additional countries connected to UCTE. In 1999, due to regulatory changes, production is out of this association due to unbundling, so it is renamed as Union for Coordination of Transmission of Electricity, not anymore production. And then part of Ukraine was connected as a Burstein Island to the rest of Europe. And then we waited till 2004. So 2004, the reconnection of the eastern part of Europe to the main grid, to the main western part of the system, started firstly with the part of Bosnia and Herzegovina. And then the rest of the region was connected back to UCT, to the rest of Europe. So at that time, in 2004, that was just 15, 16 years ago. That was not a long time ago. That was 15, 16 years ago when we had the first time in history that whole Europe was working in parallel operation. At that time, we actually got the largest system in the world working synchronously. That is more than 500 million people, 34 countries, 42 TSOs, and 3,300 terawatt hours per year of consumption. And in 2011, Turkey actually formally joined ENTSO-E, that is now the new name for UCTE. And also we have some additional candidates to join, like Moldova, Ukraine, to join this part of the system. So the main point of this slide is actually for you to get a feeling that the network was not initially designed for the requirements we have today. And not only that, it took only 15 years since we've been working in parallel operation altogether. At the moment, we have the system that is having more than 820 gigawatts of installed generation, and it's rapidly increasing every single day. We have more than 530 million citizens served. We have more than 300,000 kilometers of transmission lines. And the system is connected as given here in this figure. So why is this important again? Because we still don't have enough cross-border capacity. Fortunately, our region here in Southeast Europe is very well connected because we have small countries here in which every single interconnection lines means a lot because we have relatively low generation, relatively low demand. So one line means a lot. But the rest of Europe, especially with big countries, is not in the same position. Here you can see the level of the interconnection to the other systems as a percentage of generation capacity. So dark red color assumes that the systems like Spain or Poland is having less than 5% of its generation capacity installed in the cross-border capacity. Or in other words, only 5% of its generation can be imported. The red one, light red, is actually 5 to 10% and so forth. So you see, this is the current situation on the left side, and this is the this is a situation that is hopefully going to be actual after we implement all projects of common interest in Europe. So we need to remove red colors to actually open the borders in Europe, to have a copper plate in which everybody can trade, everybody can be connected, and everybody can run without curtailment, without any limitations in the network. In our region, in Southeast Europe, we actually performed a lot of different studies. And this is the latest one, actually, that we finalized just a few weeks ago, and it covered these countries given in blue. So from Slovenia to Greece to Romania and Adriatic. We analyzed all official development plans of the TSOs, including distributed generation, including 25% more renewables installed than officially planned. And we got these bottlenecks that could appear in the region due to this large-scale renewables integration in the region. So you can see there are very few lines or bottlenecks like a transformer station and line in 220 line in Romania, some cross-border lines here, Romania, Bulgaria, Turkey, or Albania, Montenegro, so forth, but or Slovenia to Italy. But in general, we can say that with just 22 critical parts in this huge network, in which we had more than 5,000 elements analyzed, we can say that the system is well planned, well connected, and quite robust, which is unfortunately not the situation in the rest of Europe, because the systems are much bigger with the large generation, large consumption, and therefore we need large cross-border capacity. Okay, now we have the feeling that we need to prepare a lot of projects, a lot of additional efforts to be invested in the preparation of the grid for larger scale integration and larger scale market opening. So how do we measure that? What do we say if TSO or DSO is doing their business well? When you have your telecom operator, you know very well if it's good or bad. You know how many drop calls you have. You know the signal strength. You know coverage. But how do you measure that in electricity networks business? So actually, we have three groups of quality areas. The first one is commercial quality. The second one is continuity of supply, and the third one is voltage quality. Part of that is covered, is the responsibility of the TSO and the DSO, while part of that is covered by the supplier. I don't want to go into details, just for you to get a feeling that we have a lot of maybe 15 different indicators which the regulator is supposed to follow, to measure, to define at first, and then to see, okay, this is a threshold, this is the standard value, and you need to be better than that. For example, better than given unplanned supply interruptions, frequency or duration. So you need to be better than that, and then you'll get the award or you get a penalty if you're not fulfilling that. Why is this measuring of quality of TSO or DSO service is important? Because half of the this is the list of the official reports that were given in last maybe 20 or more years. So before this additional requirements on the network from the renewables integration and market opening side, which says, for example, in late 80s, 90s, that half of all computer problems and 1/3 of all data loss can be traced back to the power line. Or manufacturing company lost more than 3 million one day last summer in Silicon Valley when light went out. Or Berkeley Lab study estimates that 80 billion of annual cost due to power interruptions, or 30–40% of all business downtime is related to power quality problems, or 50 billion per year in the US is lost as a result of power quality breakdowns. As you see, this is mostly for the US system, but the situation is comparable in other developed countries. So we can say that the network is playing a very important role in not only in our sector, but also in economy as a whole, in numbers. So how do we measure it? We can measure it on two ways. The first one is the system level, and the other one is individual level. Of course, both approaches have advantage or disadvantage. So if you measure quality of your system operator on a system level, you have just one number. Like Slovenian DSO is doing well. We're having rates of, I don't know, 4.2. And this is, as always, statistics. So you can have some areas which are really poor, and you can have some areas that are really excellent. And the average is 4.2. But much better approach is on the individual level, when every single customer or network user is having its own indicators where we say, okay, this area or this customer is having really good service, the other one is not, and therefore we are going to the other one to make it better, to improve it. So the other problem that I wanted to point out is actually that this quality of service was introduced first in Italy 20 years ago. So before that, simply there was any measurement or official, framework to follow that. Even today, a lot of countries, especially non-EU countries, don't have these indicators or standards in place. How it works in reality, this is the graph where here you have quality and here you have reward, financial or penalty. So you have a performance standard, and there is a threshold between plus and minus to the performance standard in which the operator is getting nothing. So if you're a little bit better, a little bit worse than performance standard, then you are okay. But if you're doing it better, much better than performance standard, then you can get some reward, as given in these examples of Hungary, Portugal, and Italy. So different principles, different curves, but the same principle. Same on the other side. If you are having, let's say, more interruptions than the standard requires, then you have to pay the penalty. And this is, for example, Portuguese case in which there are 5 million euros per year available to the TSO. So the regulator is approving that. They define this energy not supplied reference value. This is the value of the electricity that is not supplied due to outages in the network. So if you're doing a little bit better or a little bit worse than that in this area defined as 0.0004 times, no, this is that band is 12% plus and minus. You are doing okay, but if you are better than that, you will get incentive, and this incentive can be at maximum 5 million per year. If you're doing worse than that, you have to pay the penalty, and that penalty is at max 5 million per year. So this is the principle. They calculated these numbers based on some local specifics, but this is the way how to motivate the system operators, both TSO and the DSO, to follow their performance, to measure their performance, to improve it, to get rewarded or penalized if they're doing good or bad. So this is also something that is additionally, that was additionally needed, somehow to push system operators to serve better. The third topic that I will cover today, I know that it's maybe a little bit too much or too fast, but if you have any question, of course, you can interrupt me anytime. So the third point here that is important in renewables integration and market opening for the networks is the problem of ancillary services. By definition, these services are something that is required by the system operators to enable system integrity and stability, as well as the power quality. for those that are not familiar with it, just some analogy with lake. So you have the power system. Let's say that is the lake. And the water level in the lake should remain the constant. Let's say that is the frequency, so the level of water. But at the same time, you have a lot of streams, downstreams, and you have a lot of inflows. And all these inflows and sinks are quite, how to say, random. So you cannot control them 100%. So you need to have some reserve somewhere aside to add some water or to take some water from the lake to keep the water level the same all the time. That is ancillary service. This reserve from aside is the ancillary service in the system that helps you keep the water level constant. The problem is that this reserve actually is not a DSO TSO property. So they need to purchase that, they need to organize the mechanism, they need to regulate all that and so forth. Why is this important? This is a clear evidence that happened a few years ago with the PV generation in Europe, when we had the solar eclipse with 17 gigawatts of drop of the generation in just half an hour or so, and then 26 gigawatts of increase in just another hour or so. So in Europe, actually, we had altogether, you see, minus 17 plus 26 gigawatts of in just a couple of hours, or maybe 2 hours. So this is really challenging task for the system operators, because they need to find a replacement in all these periods, just to keep the level of the water in the lake at the same value. And this is not something new in the system. Actually, we had that from the very beginning. This is one interesting case from 1990, when the Football World Cup semi-final was going on that was, I think, in Italy, this World Cup, when England was playing versus Germany. And this is the system load in UK. So the match started actually in 7 p.m. and this dotted line is actually planned load of the system. When the match started, the load actually dramatically dropped for almost 3,000 megawatts, because everybody was watching TV and nobody was doing anything else. In the halftime, probably people went to the toilet or go to the fridge or whatever. And then 1,600 megawatt increase in just these 15 minutes. And then with the second half, it dropped again for additional almost 3,500 megawatts. And then, unfortunately for the system operator, there was an extra time. So they had another jump here and then another decrease here. And then end of the first extra time is clear here how it affects the system load. And then following penalty shootout and the end of TV transmission is again increasing the system load quite dramatically. Probably England won this one, or maybe not, I don't remember. So this is the problem of the frequency control in everyday life of the system operator, but now with the TSOs, it's with the renewables integration, it's getting even more challenging. The point is here again the same. We have no big history on that. Ancillary service history is given on this slide. So red ones with the UK was the first one that introduced ancillary services mechanisms like 20 or more years ago. The other countries, let's say around 15 to 20 years ago, and the green ones 15 to 10 years ago, and the rest of the region, Eastern and Southeastern Europe, actually introduced these mechanisms just 10 years ago or less. What is the situation now with the renewables? It's getting worse, I would say. So due to large-scale wind integration in North Germany, when the wind blows and when the generation is huge here, there is spilling of energy across the border. So these arrows represent some surplus of the electricity in German system that goes these ways through the neighboring countries. So Just remember that the massive renewable generation in Germany is on the north and consumption on the south. So without enough infrastructure in the middle, I suppose. I'm not familiar with German details, but it seems to me like that. And the large part of the electricity flows to the neighboring systems. And these arrows are actually numbers of megawatts that were different than initially planned. And this is why these guys on western borders installed phase shift transformers to better control these unplanned loop flows. This is also an interesting case between Germany and Poland, when actually these values show what is the unplanned flow in one or the other direction. So the green one is average mismatch between planned and realized flows cross-border between Germany and Poland. And you can see here the numbers in all these years is around 1,000 or even 1,500 megawatts. So we have 1,500 megawatts more going across the border than planned. So this is the challenge for all operators. And this is also some interesting indication that is now recovered, but these first years of large-scale renewables integration somehow had an effect, or maybe it's not linked directly, but some analysts said that it is. So this is the frequency on European power system along since 1995. That was somehow related to larger scale renewables integration. So the frequency is changing, and it's outside the range 49.9 to 50.1. So this is our water level in the lake, and it's not quite constant. If it's ideally constant, that would be 0 all the time. But this is the graph that is showing how much time it is out of the ideal position, and it's growing. So for example, at the end of 2013, we have 2.5% of a time per year. That is almost 9 days altogether during a year when the frequency was out of this regular range. Of course, this problem was introduced in 2000 maybe, and 10-15 years we were dealing with it, but now the system is getting back to normal, and the frequency is not that much out of the wanted range, even though we had some strange situation in 2018 and 19 with the frequency deviation, but that's something else. And the last part, I hope you are still there, is network planning. So we need to be careful with the network planning, simply because the uncertainties that are present now are much higher than ever. It takes years to construct, to prepare, to construct, to finance one single network element. And especially nowadays with the growing, environmental requirements and special planning issues and so forth. So let's say that we have, this is just one simple example. If we have a system like this one with 2 generators and 1, 2, 3 consumptions, and these are the lines between these nodes. So if we put a system running, we will find that this line is overloaded. If transmission capacity is 300 megawatt, let's say this simple exercise shows 333, which means that it is overloaded. So in normal conditions, we will construct another line here. But if we construct it here, and if we have different bidding of the generators, so different prices of these 2 guys here, the power flows, of course, will be changed, because you will engage more the generator that is cheaper, right? So if you change this pattern of the generation, now this line will be overloaded. And then we need to increase the capacity here on this line. So it is additional effort to the system operator. But what if here, for example, we have an additional generator constructed in this node here? Then it changes it completely. So we don't need any network reinforcement here. So the point is that actually the system operators, both transmission and distribution, are faced with a lot of uncertainties in the system, and they need to invest huge amount of money. And this is just one example of the ENTSO-E 10-year network development plan, in which these are the countries that are having their own investment plans. But the network investments are divided in three groups. The first one and the biggest one is renewable integration needs. And we need to construct in Europe more than 45,000 kilometers to absorb renewable sources as planned. We need to construct 22,000 kilometers for security of supply and 18,000 for market integration. So we can say that 150 billion euros needed for just for transmission, for high-level transmission network in Europe in next 10 years, and 52,000 kilometers of new lines. A large portion of that, 87%, is related to renewables. So this brings us back to my starting note that the network was not initially planned for all this, and we need to invest a lot to prepare it for the operation as we foresee in near future. Just for you to get a feeling, what is the level of investment needed here is given on this slide. So this is the percentage of the levels of project values. So light green is projects with less than 300 million, and dark green is more than 1 billion, you see here. So 46% of the project display costs more than 1 billion. So no mistakes are allowed, even though we have a lot of uncertainties, So the good news is actually that the impact on the bills for the final consumers is not that much, just maybe 1% or so. That is 1 to 2 euros per megawatt hour, which is not that much in a final consumer bill. Just to recap, so the network planning uncertainties are related not only to new power plant size and locations, as we saw in a simple example, but also on the load growth, renewables integration, future market transactions, generation dispatch, electricity market prices. Everything is having impact on the network planning, because if any of these indicators is different, inputs is different, it could result with a different topology needed. And just as my last slide, it's not only that kind of uncertainty. This is just one illustration. What is the pressure on the network expected in the future? Today we all have Google, of course, and if you type one term in a Google and press enter, then you will activate some servers, some computers, some additional equipment, and that electricity needed for your one search is actually enough to light 60-watt power light bulb for half a second. So the electricity is estimated like 30 watt seconds. But the amount that Google searches in 10 minutes, all Google searches around the globe, is actually enough to light Las Vegas for half an hour. So with these new technologies, with these new gadgets, with this new modern way of life, especially in COVID, we will all put much bigger pressure on the networks. Not to mention new technologies such as cryptocurrency and so forth. For example, electricity needed for mining of Bitcoin today is equal to the total consumption of Switzerland per year. So it is really a huge challenge, not only in renewables, not only in these new technologies, but also coming technologies that are in front of us, like all you follow and all you know. So I'll stop here. I hope I didn't took too much time. And if you have any questions, of course, feel free to ask or comments.
So, thank you very much for this super interesting presentation. It's a great introductory, let's say, presentation for, and I would like to invite our next speaker, Professor Tomislav Capuder. I also wanted to inform you, I'm sorry, I forgot to tell everyone that the sessions are being recorded. So if there is any issue in this regard, feel free to inform me by sending email or here in the chat. So let's continue with Professor Tomislav Capuder.
Thank you, Mati. I'm just having some problems finding my presentation, which was perfectly fine a minute ago. Do you see my presentation now?
Yes, it's here.
Perfect. Just give me a second. And you see when I scroll, right?
Yes, it works.
Okay, sorry about that. I just wanted to make sure that everybody sees what I'm presenting and can hear me perfectly. So thank you once again, and good morning to everyone. And special thank you to Professor Majstorovic, who made an excellent introduction and a very interesting lecture, which perfectly serves as introductory to only two projects, which I'm going to present today out of a larger portfolio of different projects that we are currently running in my research group. So I've tried to visualize them in this slide, with starting with these educational ones. Of course, we are a faculty, so our core business is educating future engineers. But moving up is more like research and application, so research and innovation actions, growing from regional ones to the European level, and going down research projects. And of course, the last but not the least part is putting all those research projects and developments into the hands of the industry, of our industry partners, and actually developing products which they are going to sell in the near future. So as you can see, these are the four main pillars, as I would call them, of the research and innovation that we do at the faculty or at the Department of Energy and Power Systems. And today I will focus mostly on these two projects. So the two projects coming from the Horizon 2020 funding program. So as you can see, they are more or less structured in a similar way. They deal with the smart energy solutions. With this pillar, I'm trying to capture basically everything that has to do with the network infrastructure or with the integration of different energy vectors or sectors. So integration of multi-energy systems, also batteries and storages, which are the topic in the FlexiGrid, and novel markets and business models in the ATTEST project, which focuses on the interactions between the transmission and distribution system operator, going from operational to the planning aspects, to some very interesting tools and pilot locations where we will try to test these tools. So both of these projects actually started, I'm going to say recently. We are still in that initial phases, with the first year gone in both projects. So the first one is called FlexiGrid, interoperable solutions for implementing holistic flexibility services in the distribution grid. As the title says, is focused on the distribution networks. It includes several distribution system operators, companies developing solutions, and research institutes developing innovative models, softwares, algorithms, which have the goal of enabling all those aspects and challenges that Professor Majstorovic mentioned in his presentation. So increasing shares of distributed generation, but not just distributed generation, also electric vehicles, integration with different energy infrastructures, electrification of heating. So all these challenges that arise in the distribution grid, which were basically scarce or not present, I would say, less than 10 years ago. So the FlexiGrid project is an innovation action. I believe most of you are familiar with this, but this basically means that we are building up on the existing tools and adjusting them and further developing them, but the emphasis is on actually putting them to work. So making sure that these tools actually work in reality and not just in a simulation environment on our computers. So essentially, we have the first 22 months or something like this to finalize and develop the tools, but the rest of the project is dedicated to implementing those tools on real-life locations and on real-life grids, and to see how our tools work and if they actually do what we say they do. From the map, you can see there's a variety of European countries involved in the project, but the blue countries actually provide also the test locations or the pilot projects for the developed tools. So the main goal of the Flexibi grid is to allow the distribution grid to be able to integrate a large share of variable generation, which is apparently mostly present in the low and medium voltage networks. So while the wind power plants are probably more integrated in the entire Europe on the transmission level and are related to the issues and challenges that Professor Majstrovic was mentioning, the PV, the EV, and the electrification of heating happens on the distribution level on the side of consumers. These consumers traditionally would know and care about the electricity as much as there's electricity in my outlet. And suddenly, 7 to 8 years later, everybody is being encouraged to have a PV on the rooftop, to care about when they spend the electricity, how much does it cost. They are, in some recent EU packages, encouraged to participate in the system services and to actually get money for the services they provide in providing either security or stability of supply. And to do so, you need to completely not just redesign the distribution network in terms of planning, but create some significantly different tools for the operation of the distribution grid. These tools need to provide flexibility, so use the resources that they have from the third parties, so the parties which are different than the distribution system operator. They need to ensure that the distribution network, which was more or less always very reliable in its operation. We saw some indices from the previous presentation, but in general, in urban cities, which are the pilot locations for this project, you had a high reliability of supply for the end consumers. We want to achieve that regardless of the new technologies that you are trying to integrate into this distribution network, which is passive and single directional one, that the reliability remains at least the same while the distribution grid transforms into a bidirectional and active distribution network. And of course, the economic efficiency. So everybody wants lower bills, and these new technologies actually enable them to maybe even create some profit by providing system services. We focus on 4 demo sites, and we develop some solutions for them. In general, the FlexiGrid project is divided into 9 work packages. The ones that I will mostly describe are here in the work package 4, but in general, we make sure the public is aware of what we are doing in work package 2, especially since we have some buildings and some end consumers involved in terms of demand response. Then we are developing the physical architecture. This means the hardware solutions that are going to be developed from the existing ones and implemented in the pilot locations. We develop some very interesting software tools, some modules, some operational assistance to the distribution system operator. One of very interesting aspects is this work package 5, where everything is integrated into a single platform which enables this interoperability, and so on. We have demonstration campaigns. We look into how to replicate this, not to have this only on these 4 locations. So work package 7 and work package 8 are basically connected, where we base these replication business cases and potential exploitation strategies to upscale this and ensure that the companies who are developing these solutions with us in the project actually can make money of this in the future. And of course, in the last one, this is what we are doing today, communicate what we are working on and disseminate it to every interested stakeholder. So we have 4, well, actually we have 8 goals, but 4 by 4 to improve the power system flexibility, the observability and controllability. I think the first one is maybe more familiar one because the last presentation gave a perfect introduction to this. So we have different new technologies. These technologies are less controllable than the conventional ones, which we are used to and which we know how to operate. And we actually want to utilize the flexibility from these new sources so that we do not overbuild the network, or that we do not get ourselves into the position where we cannot integrate these new technologies because, as Professor Majstorovic nicely said, it takes years to plan, develop, and build new capacity in the networks. So we are trying to optimize how the network works by utilizing the flexibility from third-party participants. Of course, when you do this in the distribution network, it's a particular challenge. When you go to the lower levels of voltage that you go in the distribution network, the observability, controllability, and automation is lower. So basically, at the transmission level, you could more or less confidently say that you have these aspects covered. But when you go to the medium voltage, it becomes a bit scarce. At the low voltage is very low to non-existing, depending on the country and depending on the region in a specific country. So in rural areas, you will very rarely come up with a smart meter or any kind of measurements in the low voltage network. Traditionally, this was not needed. In the new concepts or the developments that are happening in the distribution networks, this is definitely needed. As said, the first goal, the flexibility, is connected to the third goal. You need to, if you integrate these new technologies into the network, which was built for single direction line flows, you occur congestions. These congestions are not just current congestions, so it's not just connected to the lines that you cannot push the electricity or the current through the lines. Is also probably even more connected to the voltage issues and the deviations of voltage in the distribution networks. And we are looking into ways of mitigating those in an economic, efficient way. So again, if you develop multiple solutions, they should not be just separate tools, which you need to, you have to run in a non-coordinated way, but we are working on interoperability and compatibility of these tools. We are carrying out the demonstrations to bring it up to level 4, to technology readiness level 4, meaning that they are ready for replication and market development. So selling those solutions actually to different stakeholders outside the consortium, and also the things that are very often neglected in engineering project, which basically this one is increasing the awareness of the citizens, the stakeholders. This is one of the challenges that I presented also in the first slide. Regardless what you think you need to do with these new technologies, they will actually not become flexible, and the end users or the citizens will not participate willingly in these new services, meaning that the tools that you've developed are basically useless unless you educate them, you demonstrate the opportunities and the possibilities that they have. And this is one of very important goals that we are trying to achieve in the project. So as I said, we have 8 or more or less 9. So the 9th is integrating the 8 into a single platform. 9 solutions that we are offering. So the 4 are hardware solutions, the secondary substation of the future, meaning that we increase the observability on the low voltage distribution network, and then this is used for everything that we do on a medium voltage network. Some smart meters with the feeder mapping capabilities. Again, these smart meters are not the smart meters that are going to be placed with the end consumers. These smart meters are what we call in Croatia more like concentrators of what's happening in the low voltage. So they are mapping and recording the measurements from the low voltage network, but they are placed in the substations of medium to low voltage networks. Very important is this part of the protection for high renewable energy sources penetration. This one is related more to ensuring that if you have an issue and you have a problem due to these two-way power flows that you have now in the grid, that you minimize the interruption time, but you maximize the welfare or the security of service for the end consumers. So you're doing two things here. You're trying to develop modules and algorithms to detect where the fault is. If you are able to do this, you are able to quickly repair the damage. And the second one, maybe the more popular one or the more media present one, is the development of the self-healing networks. The energy box, this one will be placed on different locations where we have the end users participating in our tools. And then, as I described, we have software models connected to this solution 3. So the 5th one is fault location and self-healing. The 6th one is oriented towards using the data that you already have in the grid or that you're going to collect with these new hardware, so solution 1, 2, and 4, to use the data and to do what you basically don't do today in the distribution network, to predict and to accurately forecast the consumption, the production, and to better manage your network. So these forecasting tools are going to be done in a very narrow time span. So they're going to be from 1 second to 15-minute intervals for the 15-minute ones for the day ahead or 3 days ahead. So they're connected more to the operational aspects than to the planning one. The 7th module is the congestion management. So as I mentioned, once you have, for example, a lot of PV, you might encounter voltage problems in the distribution network, with voltage going from the upper boundary to the lower boundary of the allowed voltage constraints in a matter of hours. But also, for example, if you have new consumers such as electrification of heating in the buildings, or you have EVs in the network, you might encounter a current congestion in the lines. Usually, traditionally, you would go in the direction of replacing that line, building more, as we say, more copper in the network. The idea here is to develop tools which create signals to the flexibility providers. These flexibility providers are described, let's say, in this solution 8. So you use the flexibility either from the batteries, or in the solution 8, you utilize so-called virtual energy storage, which is a storage that is connected to power to heat in the buildings. So the envelope of the buildings or your houses has an inertia, which allows you to preheat or pre-cool the building and enable moving the peak of your consumption to a different period. So it's a form of demand response, but you're actually storing electricity in a form of heating energy in the envelopes of the building or the houses. The entire thing is going to be developed in this, integrated in this solution 9, which is shown in this slide. So the Fuse platform is is not a novelty of the FlexiGrid project, is a platform which is being promoted in multiple H2020 projects for operation of the distribution network, is a platform that serves very simply put as both the middleware platform, so meaning that it enables a conversion of different protocols and a communication of data in a unified way between different tools and different devices. And secondary is a sort of a cloud repository where you are able to store the data in a unified semantic way. So a platform which actually ensures the interoperability of all these different tools that I described we are going to be developing. So for the end, the overall methodology, we started with the data gathering and demo sites characterization. We defined how the IC architecture and the SIM definition. So this basically means that we recognize where do we get the data from, what kind of data, what kind of communication protocols are used in those devices, and what needs to be done in the Fuse platform to actually convert them into a unified model for exchange of data. In parallel, the partners are developing hardware and software solutions. So we are somewhere between the step 2 and step 4, which are more happening in parallel, but the step 4 is behind the step 3 because these solutions all need to be integrated into the Fuse platform. And what's ahead of us is validation, demonstration, and replication of the strategy. So the first project that I presented is focused on the solutions for the distribution grid. And if you remember, it's innovation action. The second one is called a test. It's advanced tools towards cost-efficient decarbonization of future reliable energy systems. A test is research and innovation action. So going from something where we know the tools, but we want to enhance them and put them into action in reality, to a project where we are, I'm going to say, inventing tools. So some of these tools exist to some part in research literature, but it's very questionable if they can be scaled up, if they actually can be made operational in reality. And in research and innovation actions, unlike the previous project, the emphasis is on research. So in this line, we spent half of the project actually developing the tools. The other half, we are testing the tools, emphasizing that we do not need to reach the TRL 8. We just need to test the tools and see, okay, so this research that we are doing actually makes sense. But also, we are not going to keep this within the research community, although you see on the left-hand side of your screen are the research institutes involved in the project. So again, scattered all over Europe. The project consortium is led by Inestec from Portugal. On the right-hand side are the companies, and as you can probably notice, is very Croatia-oriented. So all the pilot locations, all the testing, if these developed tools work, will be done on the Croatian distribution networks and transmission networks. So we have our distribution system operator involved, our transmission system operator involved, and one of our SCADA IT companies, which is maybe to all of you more known by being one of the world-leading producers of transformers, but rest assured they're one of the leading partners in developing on SCADA and IT solutions as well. So while we develop the solutions, these guys test them. The TechRain, which changed the name, so it's now Alcatel, is actually putting this together into a single platform together with a partner from Croatia, Končar. So Končar is more familiar with how Croatian system operators work in terms of IT. So they are support of TechRain in putting this platform containing these tools into operation in our system operators. So again, we have 8 work packages, similar to the previous one, but here the 3 ones that are here in the center of the diagram are the key ones. So as you can see, we are actually going from work package 4, where we are developing operational tools. The operational tools are focused on coordinated operation of transmission and distribution systems. As you remember from the last project that I presented, the FlexiGrid, we focused on distribution system operator and distribution network using the assets to improve its operation. On the other hand, the aspects that were presented previously by Professor Majstrovic, you see that on the level of transmission or the entire system, there's a need for these new resources, distributed energy resources, which are being built faster, which have the capability to provide different services. There's a high interest by the transmission system operator to actually use these assets and provide more stable and more secure supply of energy and the stability of the entire system. So we are looking into how can the transmission system operator buy or procure frequency congestion management services from the distributed resources. And then, of course, the story becomes very complex. The transmission system operator communicates with a bunch of small resources which are scattered over the distribution network. And you cannot really just procure services from them and ignore the distribution network. You need to coordinate if providing services from these resources actually harms or puts the operation of the distribution network into jeopardy, because if you get the service for the entire system, but you actually create a problem on a lower level near to the customer, you didn't do anything. So this is very complex. You actually have very, very complex optimization tools being developed here. So we are developing so-called optimal power flow, AC optimal power flows on a day ahead and in real time for both the transmission and distribution system operator and trying to coordinate them. We have a tool which is dealing with the state estimation, and we have a tool which is dealing with the online security assessment, so that you actually can assess the needs for frequency services. The work package 4, which is dealing with the operational aspect, is closely connected to the work package 3, which is going more into the planning aspects. You will now recognize that we are doing a huge jump, let's say, from the complex aspects of planning, which Professor Majstrovic mentioned. Here, we are actually trying to utilize the potential flexibility which is happening on the distribution side, so that we help those congestions and planning and building new lines in the transmission level. So this is going to be a very challenging task, and it's highly dependent on the tools developing the work package 4 as well. The work package 5 is considering asset management in the power grid. So again, something that is closely related both to operational and planning aspects of the project. We are leading this work package. So some tasks in work package 4, where we are developing these tools. We are developing a tool for coordinated planning together with Inestec, and we are a link towards our system operators to actually demonstrate and assess the impact of these developed tools. So again, all the tools will be integrated into a single ICT platform for TSO and DSO coordination. The goal is to have these tools and these data open source available. So the toolboxes will be available in terms of codes, and everything can be borrowed or taken from the project website and replicated just to validate that what we do is correct. And then further on, you can build on these tools and use it any way you see fit for future development. The data, of course, will not be fully available because at the large level of data is protected and should not be available to the general public, especially the frequency data or from the transmission system operator or the final end user data on consumption from the distribution system operator. So in some way they will be clustered, but again, you will have an idea of what we were working with. The entire thing will be also nicely visualized, and what I was describing previously in work package 4 is now listed here. So these are the 6 tools that are going to be developed as operational models. They will be combined with these 3 tools developed for planning models and these 3 tools for asset management modules. So this is the concept of the energy system of the future. We put in the existing data and the data that we generate within the project. So we are, of course, preparing additional data because, as I said, some observability aspects, especially in the distribution network in 4 different countries, are not available. We put it in this ICT platform where we perform different operational and planning aspects. And this is this has the idea of minimizing CapEx and OpEx on both distribution and transmission, increase the reliability and quality of service, and decrease the environmental aspects. So these are just the outputs. I'm more going to focus on what we do in terms of piloting in the project. This is like the graph of just one of the pilot locations in Zagreb. So as you see in Zagreb, we are going to test demand response or the flexibility from buildings. We have 2 buildings which are connected to their own medium to low voltage substations. The goal is to provide frequency and voltage and congestion services to the transmission system operator. They are connected with radial lines to distribution radial lines to the transmission system. On the other hand, in northwest Croatia, where we have a distribution area of Koprivnica, we will develop tools which have the goal of utilizing the distribution system operator assets to provide flexibility to the transmission system level. So dealing with the congestions and voltage issues, this one will be a bit of a challenge. When you select the pilot locations, you always try to do it where you have the most data, but usually where you are actually rich with the data and can do these things. So provide flexibility, meaning that you have the data and also you have the controllability and automation to control these assets. Unfortunately, very usually you do not have issues with congestion management or planning aspects. In the northwest Croatia, so this is a large region that we captured, which might have some congestion issues due to the outage of the lines. I think actually it was also visualized in the presentation of Professor Meister, which is one of the 22 elements which might have a problem with congestion in Croatia or on the border of Croatia and Slovenia. This one is going to be more focusing on planning and expansion, coordinating what DSO and TSO are doing and how they are planning their networks. And that's it. These are the websites. I'm stating once again that the projects just started, but both of them already have some deliverables available. But if you have any further questions or would like to know more about the project, these 2 or other projects that we are working on, just feel free to drop me an email. This is my email address, and I'll do the best I can to answer your questions. Thank you.
Thank you, Professor Zapper. I hope we will get a lot of emails with new proposals for partnerships for the following Horizon Europe period. I would like to propose that we continue. I will just mute you. Sorry. I have some kind of background noise.
Sorry.
I don't know. Anyway, I think we should skip the short break which was planned, and continue with Professor Lombardi, and to hear the projects he is working on in this field. So please, Pio, if you can start your presentation immediately, because we are a bit out of schedule.
Just 1 second, I put the presentation. Can you see the presentation?
Not yet, but we can wait for it.
You should be able to see. Oh, I can try it again.
Try it one time.
So. Can you see it?
Yes, now it works. Just if you could make it full
Okay.
screen. That's it. It works. Thank you.
Perfect. So, good morning to everybody. I think that the presentation I'm going to show you well matched with the presentation, very good presentation that we have heard before from Goran and Tomislav. So, Bartolomeo and me and Przemysław Komaniski, we are leading since 2 years some project, the European project, which deals to evaluate and develop solutions for integrating renewables into the system. The project is called RelFlex, and is an ERANET project, which is done in Germany and in Poland. And as I said to you before, both in Germany as also in Poland, we are trying to develop solutions for integrating renewable and to create new flexibility options. In the German part, the idea is to plan and to operate factories as net zero energy. So I think most of you is familiar with the concept of net zero energy system. Our concept is a little bit different, because generally net zero energy systems means that I generate locally the energy that the system demands. But practically it works following. If you generate electricity, for example, electricity from photovoltaic, you firstly feed the network, and then you take the power from the network, which covers your load. In our system, in our concept of net zero energy factory, we do not feed the network. So we try to minimize the power that we locally generate, and we don't want to feed the network. Why that? Because we don't want to create problems to the system operator, to Goran. So if we have flexibility, so if we have a volatility generation, and if we feed with such a volatility the network, then the system operators, distributor or transmission, they have to balance, as Goran said before, using ancillary services or other flexibility options to that volatility. And that balance, it is expensive, both on operating point of view, as also on a planning point of view, because you need new lines, you need new transformer, you need new equipment. So the idea is that we try to create solutions for factories which already generate electricity using photovoltaic, for example, and we try to create solutions which allow to integrate the power into the manufacturing system. So this is one reason. The second reason is that you see here a statistic about Europe, how many small and medium enterprises in Europe already have photovoltaic plant on the roof. you see that 14% of small and medium enterprises in Europe generates locally electricity. In Germany, this percentage is something higher. In Sweden, no, more higher. Anyway, most of this investment that the factory operators have done in the last years has been done because in Germany as well as other countries in Europe, they receive incentives. So if you produce electricity using renewables, then you receive incentives if you feed the network. So in Germany, in 4 years, in 5 years, in 3 years, many photovoltaic plants will be no more incentivized to feed the network because the incentive time will expire. And the question that we have put us is, if I'm operating an old photovoltaic plant, and if I'm operating on my roof where I also have a small factory, how should I operate it after the incentive time? Actually, the German Renewable Act says that you can still feed the network, but you will not receive any incentive more. So you will feed the network for free. This is one option. Some system operators in Germany are starting to say, if you have to feed my network with your volatility, you have to pay me. So as consequence, it means that if you have photovoltaic, which does not receive any more incentive, you may feed the network. You should maybe also pay the system operator because he takes your network and you don't receive any money, zero. And then when you take the power from the network, you have to pay, of course, the power that you have taken. So the idea is that I create the flexibility inside my manufacturing system, and I try to avoid to feed the network and to integrate the power that I'm generating in my system. Of course, if the power is not enough, I can take it from the network as normal is. So for that, we have formulated a new concept of net zero energy system, the net zero energy factory, as I said to you before, which avoid or minimize to feed the network. In our case, we have a manufacturing system, and inside the manufacturing system is maybe easier or maybe more complex to create flexibility. So we have tried, first of all, we tried to create flexibility using the manufacturing system, manufacturing processes. We want to control the process. If it is not enough to compensate or to balance the volatility of a generation, then we are also planning to use a storage system, in this case battery, and we are also planning to upgrade the system using also mobile storage system like electric vehicles, which are used within the system mostly for logistic purposes, and then we can compensate the volatility of power generation from photovoltaic using these options. Another option that we are considering is the compressed air. You know that compressed air inside manufacturing system is one of the most used energy form, and there is a lot of potential to make it more flexible, and therefore we are considering also that option. The last option is to convert electricity into heat and to use the heat that you have converted for production, for production application. So we have machines that we can control, we have storage system, we have compressed air, and we have power to heat. So for example, heat pumps, which we can control. All this system is controlled by an energy management system. And what we are trying to realize is that what you see in this diagram. Before that, we start to develop the demonstrator in Magdeburg. So we have a demonstrator in Magdeburg and a carpentry. Inside the carpentry, you see here the electric schemes. We have 5 machines and we have 4 operators. Generally, for each machine, we have an operator, but for the last one, the assembly, we have, which is this one, we have, it is led by 2 operators. So in our system, we have in our mathematical model, we have evaluated the flexibility that the single process may offer, as well as the flexibility that the operators can gain by using the machines. And that has been simulated considering almost real data and considering the time that each machine needs to create different products inside the carpentry. And we have optimized it from the mathematical point of view, as you say here, with such objective function, which means we want to maximize the integration of renewable, which means we want to minimize the power which is fed into the network. You see here some equation. I will not explain you more details about it. I think the concept is clear. So at the beginning of the project, we have started to make models and to run the simulations. And as you see, this is one case, in the typical case that we have in the springtime. You have the generation of photovoltaic, and you have the power that the system consumes. So most of power is consumed not when the photovoltaic is generating. So the idea is to take this power or this load and to switch inside the time in which the photovoltaic is generating, if it's possible, or to take the surplus, that in this case you have a surplus, you have more generation, and to store such a surplus for covering the power when we don't have generation. This is a very basic idea, but to do that, we have developed as first step is to digitalize the system. So you cannot make any optimization, you cannot make any control if you cannot meter. So you know that only if you can meter, you can optimize. So as the first part, we have digitalized the system. We have created, we have installed different smart meters, and using the data that the smart meters collect, we want to better monitor the system, making forecasts of generation and of last. And at the end, we want to control the processes. You see here some the ICT architectures that we have implemented. We have here photovoltaic, we have load, we have the battery which is going to be installed, and we will also have a charging station and electric vehicles. Then we want to control the processes with giving information to the operator, and of course we want to control our flexibility options. The data are collected to use Vago smart meters, and at the end, for making such a concept more sexy, I would say, the system operator or the factory operator should also have some benefit. The idea is that the factory operator use such a solution may certificate that what has been manufactured inside his system has been done using renewable energy, 100% renewable energy. So for that, the marketing value of its product can improve. This is the idea. This is the added value that factory operator may have by installing, by changing or upgrading its system near to net zero energy factory. So you see here some schemes with Bartolome, which was has lead the ICT architecture, and you see how the system, how the smart meters work. They collect the data. The data are stored inside a database, and we can use the data for monitoring or for making prediction. The prediction. So as you see here, this is the model that we have done using an agent-based model, and that's the real data. So we have a match on what we have simulated before knowing the real data, and now you see the simulation were quite good, I would say, match very well what we have we are metering in the manufacturing system. So in this time, besides the monitoring, we also are starting to collect the data and implement intelligent energy-based algorithm for making forecasting of load and of generation of photovoltaic. So we are measuring this more or less since 2 months, so we don't have enough data for making good prediction, but the idea is to improve our prediction tool for better making prediction. Yes, and the functionality that we want to make, so we want to collect the data locally, transfer the data to Fraunhofer Institute, we elaborate the data and send messages to the operator of the carpentry. At the Möbel is a carpentry in which we are making the demonstrator. And we want to inform the operators there how they have to operate the machines in order they can better match the power generation and the power consumption. The idea is to use some colors. So, for example, we want to use the green color, which means you can continue to operate as you are doing. We will use orange color in order to say if you change or if decrease the consumption is better because you are not generating enough electricity. Or we will send information like red colors, which says please decrease your consumption. If you can, switch off the machines. So such kind of flexibility. What we are also investigating is from the social point of view, how the operators will be able to be controlled in such a way. And this is another part of the project that we will investigate in the future. So I finished. If you have any question, you can follow us on LinkedIn. The project is ERANET RelFlex. I forgot to put here the link or to put also here the logo. Maybe I can update the presentation, send you a new presentation to Matthias. Yeah, if you have any question, I will be happy to answer you.
Thank you very much, Pio, for this great presentation. Feel free to add your contact and link to the project to our chat in this group, so everyone can see it. But of course, you can also send the updated presentation. So we can continue with Professor Bartolomei Arendarski. If you can share your screen. It works. Excellent. So you can feel free to start. Thank you.
You can see it in the full modus, I hope. Yes.
Yes, we see the full screen.
So hello from my side. Let me introduce another project which we implemented in Smart Grid Plus ERANET. This project was implemented in years 2016-2018. The title is RIGRID, stands for Rural Intelligent Grid, and you see the names here, so it's a known consortium already. So what motivates us in order to implement a Rural Intelligent Grid project? As you know, the renewables energies will play a dominant role in the energy power system. If we want to meet the targets of 2050, having 80% of the total electricity demanded by RES, while installing more and more renewables is opening new challenges for the power system from the technical side, for sure, but also from the acceptance and from the economical side. So most of the projects focus, of course, on the technical issues, but we discover, and also there was the idea of the whole initiative, that we need to also take a look on the other aspects. So that's why we know that there's a big opposition for the grid reinforcement and the new installation of renewables, which need place. And we address this in RIGRID. Why in rural regions? So as you can see on the map on the right, the most regions in Europe are still rural ones. Also the renewables need place. And also, as you can see on the chart, on the graph below, the rural regions are underdeveloped in compared to the cities. That's why there's a big potential for investment there. Shortly about the consortium. We are the leader of the project from IFF. On the left side, you can see we have also company renewable energy Kraftwerke Harz from the Harz region, and also the community of city of Dadersheim. Dadersheim is so-called city of renewables. From the Polish side, the Electrum, the industrial company, was the leader. We have a university of Technical University of Warsaw. We have the European Copper Institute, and also the city of Puns. So as you can see, there was a quite good mix of the partners from the research institution, industry, universities, up to the communities. So the program itself, ERANET, addressed 3 layers. So it's a technical layer, social layer, and economical layer. Projects were obliged to address at least 2 of them. We addressed all 3. So from the technical layer, the main issue was to integrate as much as possible renewable into the local power grid in order to reduce the CO2 emissions and increase the independency and also the reliability of the power system. Social layer was, from the first side, the acceptance issues of this new infrastructure. You can see some screenshots from the tool which we developed on the bottom. But also the issues of creating new jobs in the region, keeping the people in the rural region, that they are not moving to the cities. And an economic issue, of course, is dealing with the investment. So finding the optimal business models, but also the additional issue was to open the new possibilities for the region. For example, energy green tourism or something like this. So shortly, the aims are already mentioned, and the methodology, we address all 3 layers. There was a software developed in order to optimally plan such a new infrastructure in the rural regions. This was implemented, as I mentioned it, you can see on the bottom picture in Dadersheim, which is 70 kilometers from Magdeburg, and it's very well known as a city of renewables. Because it's already have a lot of wind mills installed and PV. So they are already 100%, let's say, covered by the renewables in the year, and they are exporting also a lot of renewables. And from the other side, we have a Puńsk region in Poland, which starts already the issues related to the renewables, but they have facing the problems which Dadersheim faced for several years ago. That's why we want to transfer this knowledge and this experience to the other regions. So shortly, I will show you some results of it. So from the technical side, as you can see on the bottom left pictures, we developed a methodology in order to plan the new net zero energy district or net zero energy region. Colleague Dr. Lombardi already say about the net zero energy factory. We are, let's say, going a step further, but we start with this concept of net zero energy district in order to be fully green, let's say, at least in a balancing way during a year. I will elaborate on it later on. On the right upper picture, you can see the tool which was developed by the Technical University of Warsaw in order to optimally plan the new infrastructure in this medium low voltage power system, placement of the power mills or wind or PV, optimal corridors for connections into the power system, and later on, this optimization from the technical planning tool will be input data for the visualization, because not always the variant number 1 in the technical is the most accepted by the community there. And as you can see on the left bottom pictures, we have developed a demonstrator there. There was a water treatment plant, which was included in the demonstrator, having a PV solar panels of 40 kilowatt peak. And we have installed the battery storage system over there of 18 kilowatt and 25 kilowatt hours, and connected this all with the communication in order to make a let's say the efficient power system there. We test many use cases, starting from optimal usage of PV into the system, having like an island operation, improving the power quality. The process itself needs a lot of reactive power, so the storage can also provide a reactive power. So we were testing this, Therefore, was developed by Electrum the control and monitoring tool, which is called EMAX, Energy Management and Control System. You can see the screen on the right. It allows us to monitor all the processes in the microgrid and also to control the process in the microgrid. And moreover, this could be done remotely. So the operators are sitting 200 kilometers far away from that, and they can control the system. Okay. Regarding the economical layer, so the main result of the economical layer was the business model planning tool. So we have developed the tool in order to optimally choose the optimal business model for this region. So optimal choose of technology, taking into account the economical, weather condition, regulatory, and the financial conditions. I will not go into the details. We have written several papers to this issue, so we can provide you as well. Last but not least, we developed this virtual reality tool for optimal planning of the new infrastructure in the rural region, in order to visualize the upcoming infrastructure, in order to test and optimize the placement of the new components, and to measure the acceptance from the population living there. So as you can see here on the left upper picture, we have the wind park, which is also can be visually planned, also with some simulation of noise, of simulations of shadows, and so on. We have here on the bottom left one, you can see these new low voltage lines, overhead lines. In Poland, they are often still the overhead lines, not only the cables. And then you can see here the person which is looking on it, and then you can see the making like a simple visibility test. I will show later on this as a demo example. You see here also some small wind power generator. You can see the corridors here are visualized. We can also make a visibility test for the whole area. On the upper right picture, you can see it, where the red colors is where the new infrastructure is visible, and the green is what is not visible. So then you can, using this tool, in order to have a discussion platform with the decision makers, with the investors, and for sure with the inhabitants of this region. Normally, we have also the same problems in Germany, where the big overhead lines power corridor was built of transmission level in the touristic region of Thuringen, and there was a big opposition. And then we developed this tool, visualize this, and then the investors and the decision makers, they have let's say the platform in order to talk to the people, because they were afraid about this new infrastructure, and we, with this tool, we were able to put the level of fear to the level of fact. So we visualize this. They can see that normally the power lines will be not visible from the balcony or from the window, and they were strongly convinced in order to speed up the investment itself. So very shortly to one of the results. So the planning of the net zero energy district. As you can see, the idea was in order to supply all the consumptions with the electricity from the renewable energy generators. So converting as input, you can see, is always the electricity, and converting it to the lighting, converting this to the heating with heating pumps, converting this even to the mobility while introducing electromobility. And therefore, we have developed the scenario 2050 Punsk, where in the balancing way, the region of Punsk was able to be, let's say, net zero energy. Of course, from the thermal point of view, all the details related to the buildings, infrastructures were measured, were designed in order to make optimal thermal load and electrical load planning. I will not go into the details in it. This one was made in the simulated way while applying the simulation X, where the scenario was built, combining the infrastructure. Interesting issue is also that we didn't focus only on the electricity, but also on the other energy forms, which moves us to the very common issue, which is the multi-sectoral planning of such environments. There were simulations made, as you can see here. You can see the performances of the building types, which are to be located in this area, with the number of persons living there, with the efficiency parameters and so on, in order to optimally plan the heating pumps and coordinating the whole system. Also regarding electromobility on the right. There are some further results about the yearly consumption. So how much energy will be needed for the residential sector, for thermal sector and transportation sector. You can see this on the year simulation. The new indices were introduced, like self-system consumption index and self-system sufficiency index, in order to measure the performance of such a design net zero energy region. You can see here very shortly that the optimal solution was the maximal integration of the renewable is shown in this graph here. So this is the optimal mix also of the PV generation and the wind generation. You can see this maybe better from the next picture. So we have considered several scenarios, how much PV and how much wind. We focus on those two renewables needs to be installed in this region to make it net zero energy district. And you can see the best solution is given by the balance of 2 megawatts of PV and 5.2 megawatts of wind for this small village or small city. Also, the issue of costs. Many can say that okay, the renewables are not the cheapest source, but it's having a good, deep analysis. You can see that also for heating, even the points net zero, the cost for square meter of heating of the buildings will be not much higher than using natural gas, fuel oil, or district heating on biomass pellets. And for sure, it's CO2 free. So this few cents is worth to pay more in order to be net zero. And let me switch to the live demo presentation. I hope it's going to work. We still have a couple of minutes, I hope. Oh. You can see something that's still flashing by me. It's flashing.
We see the software, but we don't see the scenario.
Okay. Wait a sec. I will do it in the other way. I'll just show my screen. Now you can see it?
Yes.
This is the virtual development platform which we developed here at the Fraunhofer IFF in Magdeburg. We are using it for the planning purposes, for architecture planning, but also for the infrastructural planning. In this case, for the power grid planning. So you can see I'm now moving freely here using mouse. It's looks a little bit, let's say, like a computer game, but it is not a computer game. You can see here there are some new components already installed. I already download this in order to speed up a little bit the process. I have possibilities to move those lines, to rotate it, and so on. We are able also to make here some visibility tests. For example, I can make a visibility test. I will do it from the place for the individuals, because for the whole area it takes a little bit longer. Now we can the power lines will be visible from this point here, and the other parts will not be visible. It's also the parameters can be set up for that. So then you can discuss with the people if they are okay with this new infrastructure or not. We can also make some visibility tests to be seen the new infrastructure. This is, for example, the needed reinforcement or the new lines in order to connect the renewables which are planned to be built there. Therefore, we have prepared some scenarios. So we can start from the power plants which already exist. So there are the small PVs on the rooftops, which are already installed in the region of Punsk. We also have planned some small wind turbines, like of 10 kilowatt, or the vertical or the horizontal ones. We have also made some analysis for these isophone lines, like the noise will be let's say, influencing the inhabitants there or not. We were trying to find out the best place for this installation. Also, some other models of the generators were tested. I can also insert here, like, to give you some impression. This is like a regular windmill of Enercon. So if I install this new windmill here, so you can see how big it will be. For sure, it will not be accepted by inhabitants. You can see that we can make also the visibility test. We can make also some measurements test. The distance, for example, to the building. There are the regulations for this. I think that 26 meters will be not enough to install this mill here. We can make again the visibility test, for example, here from the school area. Let's place someone here. Oh, no. Sorry, I'm doing now the visibility test for the whole area. Sorry for that. It will take a couple of seconds because I make now the test for the whole area, which needs a little bit more calculation. So as you can see, there are several versions of this platform. The version for the author, so for the one who is designing the scenario, who is having the knowledge of also of the infrastructure itself. They can prepare, let's say, the scenario itself, and then there's also the version for the user, for example, for the decision maker or the local politicians, which can use this platform in order to communicate the planet investments to the inhabitants, and also now it is calculated as I escape it. So I should use this one in order to make a visibility test from the point. And then you can see where the infrastructure will be visible from this place. Yeah, also here the other components will be visible. Okay, so let's delete this windmill. Also, I can rotate it. I can move this windmill as well. Another scenario which we calculated was this Punsk 2050. So in order to supply this city, we will need 2 big photovoltaic parks. And as I mentioned, also the wind, there will be some error here, yes, of 5.2 megawatts, not kilowatts. And then we will be able to, let's see if this works. In order to supply it's also showing, we can also make some calculations regarding this economical issue. As you can see here, some pop-up windows can occur. Also, we did it for the wind and PV in order to find out the optimal business plan for that. Maybe showing you some more issues regarding to the regrid implementation itself. So as I mentioned, this small treatment power plant was made fully as a microgrid. With the photovoltaic diesel generator and battery energy storage in order to optimally operate this plant. We're also having some problem with the security of supply. This is on the end of the village, and there were some issues regarding with the problem of the power quality. Some other feature of this power plant also it is useful for the planning of the power lines. You can see here this interactive way how I can plan it. I can place some new masts. I can rotate them. if you have in the meanwhile any questions, you can ask me freely. Then this lines has to be, this mast has to be then connected. Okay, we can choose the way of connection. So several points can be here chosen, several variants can be here chosen, and you can see they're already being connected. So, and you can see here I can make some variants. I can move this, for example, in order to test the other variants of corridors. And you see the lines are also interactively moving with. I can make, again, the visibility test. I can make distance measurements. We also incorporate some, oh, that was not a good way. We can also incorporate some physics in it. So also the hanging of the lines can be measured and tested, for example, for agriculture, in order to measure the distance when the machines are working there, and so on and so on. So, yes. So also this project became already quite famous. We have received the ISGAN Award of Excellence, the action for the smart grids, international one. We received the second place for the innovative project, and also we received the first place for the prize of the transfer of this technology to the other regions. So we are quite proud of this project, and if you have any questions, if you are interested in this developments, we are very open for the discussion and for the contact. Thank you from my side.
Thank you for this really impressive, I have to say, presentation, Bartolome. I think you have quite some questions in the chat. I also find this tool as super ready for various types of implementation in not only Central Europe regions, but also in any other part of Europe. So I'm sure the tool will be easy to implement through the new transnational cooperation programs in the following period. So hope you will write some new proposals for for the new tenders that are just around the corner. So I don't know if you can maybe read these questions and then unmute yourself and answer them maybe live. Yeah, I will also stop recording because I think this discussion at the end is not so.
Yeah, thank you very much for these kind comments.